All right, guys. So obviously, as you can see, last time we had started introducing our inverse trigonometric function. So just a few things to refresh ourselves with. So remember, to be able to create these inverse functions from our original sine, cosine, and tangent functions, remember we talked about how we would need to restrict our domain on the sine, cosine, and the tangent function. So remember, the sine is limited to the domain from negative pi halves to positive pi halves. So you can see the section here on the graph, what that would end up looking like. So this little section here. For the cosine function, we limited the domain from 0 to pi. So that gives us this part of the graph. And then, of course, tangent, we are going from negative pi halves to positive pi halves. So it gives us this one branch of the tangent function. And then you can see what their inverse functions look like. We also talked about how domain and range switch places from the original sine, cosine, and tangent function to their inverses. And then you can see some of the other properties that they have listed over here. So we had started looking at, how to find these inverses. And basically one thing to remember is, this is the one here. So basically what you need to remember is that the output of each of these inverse functions is going to be an angle, right? So when you solve an inverse function, you basically get the angle where your sine, cosine, or tangent function will have that value, right? And we looked at how for the known angles, we can use the unit circle to help us out with some of that information. So let's continue from where we left off. So the next example that we wanted to talk about was this guy right here, the example 635. So you can see here, they're asking us to find the exact value for sine of cosine inverse of 4 over 5. So of course, when you're talking about cosine inverse of 4 over 5, again, remember we start on the inside with these composition of functions. If we're talking about cosine inverse of 4 over 5, remember the output for any inverse function is going to be an angle. So we know once we solve this, we are going to get an angle. So we can obviously rewrite this function as cosine of theta is going to equal 4/5, right? So we can rewrite it as this cosine function. And basically, since we know that cosine of theta is going to be 4/5, let me get my little pen here. So think about this. If we are saying cosine inverse of 4/5 is theta, we are basically saying this guy is going to be equal to theta, right? Which means we are basically being asked to find sine of theta. So if you rewrite this relationship here from the cosine inverse to the original cosine function, this is how we would define it. Cosine of theta is equal to 4/5. So you can actually use the Pythagorean identity in this example to try and solve this question here. So we have cosine of theta is 4/5. So you can see that becomes 4/5 to the second power. Of course, 4 times 4 is 16. 5 times 5 is 25. You move that to the other side and you subtract 16 over 25 from 1. And then, of course, we'll do some basic calculation over here. So you can do 1 minus 16 over 25. And again, you can solve this on a calculator. You can do it by hand. It's entirely up to you, what you are comfortable with. So we can come here and we can do 1 minus 16 over 25. We want to keep it in a fraction form. So you can see that comes out to be 9 over 25. And you can see that it comes up with 9 over 25. So now, again, if you have sine squared of theta being equal to 9 over 25, well, we want to get sine by itself. So remember, we end up taking a square root on both sides of the equation, which will give us one positive and one negative root. So you can see when we simplify that, square root of 9 is 3, square root of 25 is 5. So we have to choose between these two answers. Is it going to be positive 3/5 or is it going to be negative 3/5? So that actually brings us back to the idea that we know the inverse cosine function is going to be between the interval of 0 and pi, right? And that's kind of going back to the beginning of this section. So you can see the range of the cosine function is between 0 and pi. Or we know from the original sine function when we restricted it, we were between 0 and pi also. So it doesn't matter how you look at it, but preferably as the range of the inverse cosine function is between 0 and pi, which tells us that our cosine function, our sine value is then going to be positive. And again, guys, you can use the unit circle to help you with that. If the angle is going to be between 0 and pi, you can see all of our sine values in quadrant 1 and quadrant 2 are going to be positive, which means you are going to discard negative 3/5 and keep the positive 3/5 as your answer. So remember, again, you're going back to the domain and range to verify which answer you need to keep and which one gets discarded, right? If you look at another example here with the sine of tangent inverse of 7/4, we're going to use a little bit of a different technique to solve this one here. So for this guy, we are saying the last technique would work, obviously, but let's build up on something new. Okay, looks like one of your classmates just came in. So you've got tangent of theta equals 7/4, right? So basically, like you saw in the previous example, it's the same argument here. We can say theta is going to be tangent inverse of 7/4. And then, of course, we can rewrite it as tangent of theta should be 7/4. So the different technique we are using here, guys, is actually going to be the right triangle. So if tangent of theta, and remember tangent is defined as opposite over adjacent. Oops, sorry. If you remember from our SOHCAHTOA, so that's opposite over adjacent. So this will be the opposite side. This will be the adjacent side. So you can see in our little right triangle here, if this is the angle theta, then the opposite side is 7. The adjacent side is 4, which means we now need to figure out what the hypotenuse is going to be. And then you can see we're basically using the Pythagorean theorem to help us with that. So we do 4 square plus 7 square, which is our a square plus b square, right? And the hypotenuse is the c square. So 4 square plus 7 square equals the hypotenuse squared. 4 square will be 16, 7 square will be 49. When we add it together, it comes out to be 65, right? So you've got hypotenuse squared equals 65. And then same thing is happening. You are going to do a square root on both sides, which would give you a positive or negative root. But since you are talking about the side of a triangle, right, you can discard the negative sign or the negative answer and just keep the positive 65 or square root of 65. So you can see that's where the hypotenuse is a positive square root of 65. So now we have the 3 sides of our triangle. And based on that, we can now find what the sine value is going to be. So let me just clear up some of this writing to make space. Okay. So now that we know the 3 sides of our triangle, we can find sine of theta. So think about this sine of theta. Again, remember we defined sine as opposite over hypotenuse. So if this is the angle theta here, the opposite side is 7, and the hypotenuse, as we just calculated, is square root of 65. So you can see, guys, they are leaving the 65 square root on the denominator. But again, in algebra, we do not leave the radical on the bottom. So you need to rationalize your denominator and write it as 7 times square root of 65 over 65. So rationalize your denominators when and where you can. And then you can kind of see your textbook just says that basically sine of tangent inverse of 7 over 4 is equal to sine of theta, which again comes out to be 7 over square root of 65. And as a rationalized denominator, that would be your final answer. Everybody okay on that one? So two different techniques, right? We're using the Pythagorean identity with the sine square plus cosine square equal 1. Or in this example that we just saw, we are looking at using the right triangle and then using the Pythagorean theorem to help us simplify this example. So something similar happening here in 6.3.4. You can see now we are using cosine with sine inverse of 7 over 9. So same thing, take your inside function sine inverse of 7/9, set it equal to theta, which means we are now given sine of theta is equal to 7 over 9. And you will see we went back to the Pythagorean identity of sine squared plus cosine squared equals 1. So this time we are given the sine function 7 over 9. So as you can see, that will become 49. 9 times 9 is 81. And then obviously, same thing, right? You're going to subtract that from 1 on the other side. So we will get 1 minus 49 over 81. So let's come back here. 1 minus 49 over 81. We'll change that to a fraction. And you can see it's coming out to be here, 32 over 81, right? So you've got 32 over 81 for our cosine squared of theta. And then same thing as we saw before, you will need to take a square root on both sides. So that will give us plus or minus root. Of course, these guys will cancel each other out, giving us cosine of theta. Now, you will see that this is not, because from the answer, you can see this is not a perfect square, right? The number on the top, the 32, which means you have to simplify your radical. Now, 81 is a perfect square for 9, so that guy will actually simplify. But from 32, we need to see what perfect square we can bring out. So if you think about it, we can rewrite 32 as 16 times 2. 16 is a perfect square, so you can actually simplify this into square root of 16 is 4. Square root of 2 will stay under the radical, right? Because 2 is not a perfect square. And then square root of 81, of course, is 9. And again, guys, we're still using the same logic of why we are looking at a positive answer and not the negative. Because remember, again, the range of the the range of the sine inverse function is, no, we've got cosine on the outside. Hold on, I'm confusing myself here. Because we have the inverse cosine on the inside, but we have sine inverse here. Okay, so for the sine inverse function, which is on the inside, you can see for the sine inverse function, your range actually is going to be between negative pi halves to positive pi halves. So that's, of course, going to be quadrant 1 and quadrant 4, right? But since the cosine function can only be between 0 and pi, that actually tells you you're looking at a quadrant 1 value here. So with the cosine function being on the outside, you are going to only keep, where is my example? There we go. So that's why you are only keeping the positive solution over here. So again, just using the domain and range for your functions to figure out which answer you keep, and it's going to be positive for this guy again. But yeah, I mean, you can see we kind of went back to using the Pythagorean identity over here when you're working with sine and cosine functions. If you look at this next example, now this one is going to be a little bit different if you just compare between 634 and 637. Here you were given an actual numerical value, right? We had a fraction of 7/9. But look at the example for 637. It's actually giving you an x value instead of a numerical value. So it's giving you an expression of x/3, and then they're telling us x is going to be a value between -3 and +3, including the endpoints, right? So now you are actually dealing with an algebraic expression, but our process for solving it will be very similar to what we've done in the previous examples. So again, since you're starting out with the sine inverse function on the inside, we know that's going to give us an answer of theta. So you will basically end up with theta equals sine inverse of x/3. And then, of course, our x is going to be between negative and +3, including those endpoints. So you can use that to rewrite the sine function now, right? So we can rewrite it as sine of theta is equal to x/3. And then using the Pythagorean identity instead of the theorem, this should actually say identity. So you were using sine squared plus cosine squared equals 1 again, right? So now you can see, since we are defining the sine of theta as x/3, you use that to substitute in your equation, in your identity here. Now, of course, x squared will give us x squared on the numerator, 3 squared will give us 9. But now you will see, of course, we end up subtracting this on the other side from 1, and you end up with cosine squared of theta is equal to 1 minus x squared over 9. So here you will see we do actually find a common denominator to simplify this. So you will multiply the left-hand side with 9, which will end up giving you 9 minus x squared on the numerator. You have a common denominator here, so that becomes 9. And you can see that's where the 9x squared over 9 came from. Since you are doing cosine squared, you of course end up taking a square root on both sides. So if I just replace this with cosine squared of theta here, you're taking a square root, which again will give us 1 positive, 1 negative root. And you can see how we simplify that. Oh, okay. Zadek, if you think logging out and logging back in may help, I would say try that and see if it helps. Unless you think it's just an internet, connection issue. And then if you do get kicked off, just I would say try logging back in when you can, okay? But thank you for letting me know. All right, guys. So yeah, you can see now again, we are basically at cosine of theta equal to positive or negative square root of 9 minus x squared. And then, of course, on the denominator, you can see the square root of 9 can simplify just into 3, right? So we can go ahead and simplify that denominator. And then when it comes to choosing, do you have a positive or a negative root? Again, we know the sine inverse function must have an angle between negative pi halves and positive pi halves. So just like we saw in the previous example, that tells us the cosine value is actually going to be positive. So drop the negative root and keep the positive one, and you can see the solution comes out to be that positive square root of 9 minus x squared, and then the whole thing divided by 3. So this was with an algebraic expression. Did anybody have questions on this particular example here, or just in general, the other examples we've talked about? No questions so far? Okay. Just one more example with that algebraic expression here, guys. So you can see this time we are given sine of tangent inverse of 4x. And the x is defined as a value between negative 1/4 and positive 1/4, of course, including the endpoints again. So start by rewriting your tangent inverse of 4x equal to theta. We can then simplify this into tangent of theta is equal to 4x. Now you will see they went back to using the right triangle over here. So of course, if this is our angle theta, and we write that tangent theta of 4x as 4x over 1, then remember the 4x will represent the opposite side, the 1 will represent the adjacent side. So you've got on the opposite side 4x, adjacent side 1, and then of course we go back to finding the hypotenuse, right? Using the Pythagorean theorem over here. So they kind of skipped that step. So again, if you had to do the Pythagorean theorem, you would take the 4x and square the whole thing, plus 1 from the adjacent side and square that. And then, of course, now we have to figure out what the hypotenuse is going to be. So 4x quantity squared, 4 times 4 is 16. X times x is squared, plus 1 will give us the hypotenuse squared. And then again, you can see that we will need to get the hypotenuse by itself. So you can go ahead and take a square root on both sides, which will give us, again, a positive and a negative root. But remember, again, since we know this is the side of a triangle, you can actually drop the negative and just keep the positive answer, right? So we wouldn't have to worry about the negative side. So now this is telling us the hypotenuse of our triangle is actually going to be square root of 16x squared plus 1. Your textbook left it as 4x quantity squared, but you can expand it out to 16x squared. Okay, so now that we have the three sides of the triangle, we can now come up with our sine of theta value, right? So sine, remember, again, is opposite over hypotenuse. So you can see the opposite side is 4x. Our hypotenuse is square root of 16x squared plus 1. For the algebraic expressions like this, where you have x as part of your answer, they will actually leave the radical down on the denominator, because the idea is if x were a number such that that expression on the bottom could be simplified, then you may not have a radical in your final answer. So in this instant, you can leave the radical on the bottom if you want. However, guys, like I showed you in that previous example, here, when you're just dealing with directly with numbers, you do want to rationalize your denominator. So if you have an x in the expression, it's okay to leave the square root on the bottom, but if it's only numbers, rationalize it. Alrighty, so that was the last example from this section, but I did have a couple of examples I wanted us to work on. So how about, let's do one with a number, and then we'll do one with the algebraic expression. So let's do cosine and tangent. So number 25 here. Did that get hid behind? Yeah. So let's look at number 25 from the textbook here. So you can see this is a combination of cosine and the tangent inverse function. Okay, so obviously you want to start on the inside because we know that's going to give us the angle theta. So you would have theta equals tangent inverse of 4, which we can then rewrite as tangent of theta is equal to 4. So how would you proceed from here, seeing how we did in the other examples? What would your strategy be here? So remember when we were working with sine inverse with cosine or sine with cosine inverse, we could use the Pythagorean identity. But then when we're working with tangent, remember the tangent Pythagorean identity goes with the secant function. So we can't really use the Pythagorean identity here. But what else can we use? And you've seen the previous example, so hopefully you have an idea of what we need to do here.
You can just use the ratio that tangent is, so the opposite over adjacent. So tangent theta is equals 4. So you go to 4/1.
Yeah, very good. So basically, yeah, go back to your right triangle like we did with the other examples. If this is our angle theta over here, remember you can write this as 4/1. So this will become the opposite side. This will become the adjacent side. So you have 4/1. And then, of course, you are trying to figure out what the hypotenuse is going to be. So this is where you bring in your Pythagorean theorem. So that would, of course, give us, let's see, 4 squared plus 1 squared is equal to the hypotenuse squared. And as you can see in this case, 4 squared would be 16 plus 1, which is 17. And you would have 17 as your hypotenuse squared. And then obviously, like we saw before, we need to get a square root on both sides. Since this is technically, again, the side of your triangle, you can just look at a positive square root of 17, right, for the hypotenuse. And again, that's really it, because once we have the hypotenuse, we can go back to the definition of the sine function, or sorry, in this case, we're using cosine on the outside. So you've got cosine of theta, which again, remember, is adjacent over hypotenuse. So that will come out to be the adjacent side, remember, is the 1. And of course, our hypotenuse just came out to be, all right, Logan, thank you. The hypotenuse, as we just calculated, is square root of 17. Now, guys, since this is dealing completely only with numbers, we will go ahead and rationalize our denominator. So this will actually come out to be 1 times square root of 17 is square root of 17. And then on the denominator, you will get just 17. So always remember to rationalize that. But yeah, once you know the technique you need to use, they are actually not that hard problems to solve, but we just need to know, should I go with the identity or would a right triangle help me here? And there's no one method. Remember, there's always multiple different ways you can do it. All right, did anybody have question on number 25 here? Are we okay so far? Yeah, all right. And then the other one, like I said, we will take one of those algebraic expression ones. So well, let's do number 29 here. So you've got sine of tangent inverse of 3x. Okay, so since we are again on the inside with the tangent inverse function, again, we can write it out as tangent of theta is equal to 3x. And again, since we are working with the tangent function here, guys, you can go back to using the right triangle again. So again, 3x will be the opposite side, 1 will be the adjacent side, and we're finding the hypotenuse again, which in this case will turn out to be what? 3x quantity squared plus 1 squared will give us the hypotenuse squared, which will of course give us 3 times 3 is 9, right? X times x is x squared plus 1. And then you end up taking your square root on both sides. And same logic, since this is the side of a triangle, we'll just look at the positive root for the hypotenuse and discard the negative root. So pretty much the same process, right, that you did in the previous example, but now we're just dealing with a algebraic expression instead of just numbers. So now you have the sine as the outside function. So since we need to solve for the sine of theta, again, remember that is opposite over hypotenuse. So this will end up becoming now, again, our hypotenuse is square root of 9x squared plus 1. So you can see again, the opposite side was 3x, and the hypotenuse is now square root of 9x squared plus 1. So I kind of hope you're seeing a theme over here. If the inside function is the tangent inverse function, in both examples that we did 25 and 29, you will see we went to the right triangle, right? Because that makes it easier to solve. But then if you look at the other examples where you had sine and cosine, inside or out, then you can actually use the Pythagorean identity method to help you solve that. So once you start recognizing these patterns, you will actually start remembering like which process you need to use. So did anybody have any questions on number 29? No? Okay. So how about,
All right, I actually have a question. I'm just having a problem with my mute button. So for the one we just did,
mhm.
when we're finding the hypotenuse by, um, we just take the square root of the adjacent side and the opposite side squared. Why are you said we can disregard the negative because because we're working with a triangle. Why is that?
So remember, this is a length, right? So you cannot have a negative number for a length because think about it as a distance, right? So it's either going to be 0 or a positive number. So that's why I was saying that because it's the side of a triangle, you can ignore the negative root.
Okay, that makes sense. Thanks.
Okay, yeah, you're welcome. All right, I'm glad you asked that. Did anybody else have any questions? Okay. And again, guys, if you come across something on homework that you need help with or you have a question, don't hesitate to ask because sometimes the examples I might do in class might look different than what you see on homework. So if that does happen, let me know. But that was the end of section 6.3. So now we're getting into section 6.4. So if you remember, we started out this chapter talking about the London Eye and how could we figure out what the height of the rider would be. And if you remember, we kind of went through that process once we talked about the amplitude, the midline, and the shift and stuff like that. We were then able to come up with equation for the height of the rider on the London Eye Ferris wheel. And you can see this was the equation that we came up with. So negative 65 cosine of pi over 15t plus 70. And in the previous section, they had basically asked us, what if we wanted to know the length of time during which the rider is more than 100 meters above the ground? And basically, to be able to identify that, of course, we need to use trig functions to solve that equation. So let's kind of build up on that now. So they're saying solving for known values, which is, those commonly known angles as we know from the unit circle now, right? So we know that we can find the sine and cosine values when they are at these commonly known angles. So obviously that same thing translates into equation. So if you are trying to solve a sine or cosine equation, solving these common angles, we can kind of use that information that we have. So look at this one here. We're saying let's solve the sine of t for equal to 1/2. But you will notice here, this time they're saying for all possible values of t, which means we are saying that angle t can be all the angles where the sine value is going to be equal to 1/2. So if you look at our unit circle over here, you will see sine is equal to 1/2 at the angle of pi over 6. And then if you go to quadrant 2, you will notice we have sine of 1/2 again this time for angle 5 pi over 6, right? So there are two angles, sorry, excuse me, that are those known angles, right? So that would be at t equals pi over 6 and t equals 5 pi over 6. However, look at the graph of the sine function here, and you can see this is where we have the value of sine equals 1/2, right? Because remember, you have the sine value here on the vertical axis, and then on the horizontal axis is your angles, which in this example, they're calling it t. So for all the places where the red line intersects the sine graph, you basically have a value of 1/2. So this angle over here is going to be pi over 6. This angle over here is going to be 5 pi over 6. And then you can see there's two more angles that are visible here. And then, of course, on the negative side, you can see four more angles where the value of sine is going to be it's going to be 1/2. So remember, we had also talked about coterminal angles. If I just take pi over 6 and 5 pi over 6 and add or subtract 2 pi from it, we come back a whole circle, right? We make a whole revolution and come back to the same value. So you will actually have infinite number of solutions for the value t or the angle t, where sine is going to have a value of 1/2, because we know this graph of the sine function just keeps going, right? Because remember, sine by itself has a domain of negative to positive infinity. So it's just going to keep giving you multiple different values. But since we know the two values from the 0 to 2 pi section of the domain is going to be pi over 6 and 5 pi over 6, we can actually use that and then use the idea of coterminal angles, where adding that full rotation of 2 pi will give us either a positive or a negative coterminal angle. So the easiest way to write it is we can say, okay, t can equal pi over 6 plus 2 pi. So we know plus 2 pi gives you one full revolution. We know subtracting 2 pi will give us a negative angle, but instead of specifying that, you actually multiply it with k, because then we can say k is an integer, right? So if k was 0, 0 times 2 pi will become 0, and you get pi over 6, which is, of course, our original angle right over here. Same thing will happen here. If k was 0, you would get 0 times 2 pi, which would give us 5 pi over 6, which is obviously this angle over here. But if k was positive 1, then that would be 2 pi, right? Which means we would complete one full revolution, which, think about it, will actually bring you back to this angle over here. If you did k equals 1 for 5 pi over 6, that will be one revolution of 2 pi, which will bring you to this point. If you did k equals -1, well, that means we are going in the clockwise direction, right? So we are going towards the negative angle, which will actually end up giving you this angle over here if k was -1. And same thing here for 5 pi over 6. If k was -1, you go one revolution backwards, and that would bring you to this angle over here. So remember, with k being an integer, k can be 0, +1, +2, +3, but it can also be -1, -2, -3, and it just keeps going in both directions, which means you would cover the entire span of the sine function by just writing it out with plus 2k, 2 pi times k on both the angles of pi over 6 and 5 pi over 6. So you will start seeing this notation more and more commonly as we move forward when they're asking us to find for all values of t or theta or whatever variable they use. So does that make sense of why we are doing the plus 2 pi k with the solution? Because to show that there are multiple occurrences, right, of the sine of t, which will be equal to 1/2. Now look at a different example here. So we're switching it up a little bit. This one is giving us a specific case. So this one is saying, okay, we have a radius, a circle of radius 5 times square root of 2, and it is intersecting the line x equals -5, which if you imagine x equals -5 is actually going to be a vertical line. And it's going to be intersecting 2 points. If you think about this, if we have a circle, and since it says -5, obviously it's going to be intersecting on the left-hand side. So you can see it is going to intersect at 2 points, right? When a circle and a line intersect. So they are saying find the angles theta on the interval 0 less than equal to theta less than equal to 2 pi, where the circle and line intersect. So we're actually going back to chapter 1 definition here, where we're saying we can actually find the x coordinate for a point on the circle by using this formula here. X equals r times cosine theta. We already know the r value because they're telling us the radius is 5 square root of 2. So you can see we can replace the r with 5 square root of 2, and it will give us this formula here. So we've got x equals 5 square root of 2 cosine of theta. Now we also know that the circle and the line are going to be intersecting at x equals -5. So again, imagine if this is our coordinate plane. Here's our circle, and here's that line x equals -5. Well, it tells you for both of these points, your x value is going to be -5, right? And then your y value will be wherever they are intersecting. So you can actually then use the x equals -5 in this equation basically and replace this x with -5. So now you can see we have -5 from the x value, 5 square root of 2 from the radius, and now we can solve that to find our cosine of theta. So isolate that cosine of theta, and you will see you end up getting basically, we would end up dividing both sides of this equation here by 5 square root of 2, right? This guy would cancel out on the right-hand side, leaving us with cosine of theta. And then you've got -5 divided by 5 square root of 2. So the 5's cancel each other out. You're left with -1 on the top, square root of 2 on the bottom. Go ahead and rationalize your denominator. Because again, guys, remember the ultimate goal is figuring out where the circle and the line are intersecting with each other. So once we figure out, okay, cosine of theta is equal to negative square root of 2 over 2, you can actually very easily find out where the two shapes will be intersecting with each other. So think about, again, where is cosine of theta equal to negative square root of 2 over 2? And you can actually come back to the unit circle for that. So you can see our cosine value is -2 square root of 2 at the angle 3 pi over 4, and also at the angle 5 pi over 4, where you have negative square root of 2 over 2. So 3 pi over 4 and 5 pi over 4, and you should see that right over here. So remember, the question was at which angle is the circle and the line intersecting? And now we have the angles. So do you see the difference between the two examples? Because this one was saying all possible angles, right? Because that was a more generic one, but this one was very specific because they said you have a circle of this radius, it's intersecting a line of this specific equation. So where will these two lines and the circle cross each other? But look at this next example. We went back to the generic formula or the generic equation, because we are saying tangent of t is equal to 1 for all possible values of t. Now, if you wanted to, think about this, when we say tangent of t, remember we can define it as sine of t over cosine of t. So if the value is equal to 1, that tells us sine and cosine have to have the same value and the same sign, right? So both numbers have to be positive or both numbers have to be negative. So come and look at the unit circle again, and you will notice that this happens at angle pi over 4, where my sine and cosine values are the same. and it will actually happen exactly 180 degrees across from that at angle 5 pi over 4, where my sine and cosine values are exactly the same. So basically, since we know the period of a tangent function is pi, you can actually use that to your advantage here. So we know one answer is going to be pi over 4, but then we know it's always going to be at that 180-degree angle, right? So you go from pi over 4, you move 180 degrees, you come to 5 pi over 4, you move to 180 degrees again, and you will now come at, what will this be? 5, 6, 7, 8, 9 pi over 4. So you will now be at 9 pi over 4, and you'll keep going, right? Now, guys, notice that at 3 pi over 4, it's not the same thing, because one value is positive, one value is negative. So you will not get tangent equals 1. Same thing is happening at 7 pi over 4. One value is positive, the other one is negative. So you will not get tangent equals 1. Tangent is only equal to 1 at 5 pi over 4 and just pi over 4, right? So that's why the 180-degree rotation, basically. So you will see when we write our final answer, we are writing it as pi over 4 plus just pi times k, right? Unlike this guy where you had 2 pi times k, but that depends on the rotation. In this example, you're just doing a 180-degree rotation. So that's why you're just multiplying k with pi, and then of course pi plus 4, or sorry, pi over 4 added with that. Does that make sense,
Would you
Logan?
need to, for that solution, would you need to add the note that k has to be an integer?
Yes, definitely. So I'm kind of surprised they left that part out, because you do want to define what k is. All right, very good. Anybody else? No question? Okay. All right, so again, let's get into a little bit of a more specific example here. So you can see this guy is talking about the depth of water at a dock rises and falls with the tide. Following the equation, f of t is equal to 4 sine of pi over 12t plus 7, where t is measured in hours after midnight. Okay, so that's important when we're working with this. So a boat requires a depth of 9 feet to tie up at the dock. Between what times will the depth be 9 feet? Okay, so we know that the depth has to be 9 feet. So that basically tells us in this equation, we are saying our f of t has to be equal to 9, because remember, they're telling us this equation gives us the depth that the water at the dock will rise and fall, right? So we know f of t has to be 9. So you can see we take this equation and set it equal to 9. And then you're trying to get the sine function by itself. So you can see we started out by subtracting the 7 first. So you subtracted the 7, which gave us the 2. And then, of course, we would divide both sides by 4. So we can get the sine function by itself. And of course, 2 divided by 4 gives us 1/2. So now we are saying, okay, we've got sine of pi over 12t, which is equal to 1/2. But if we just break this down into a little bit more generic form for the first part, then we can actually come back and look at the specific one with pi over 12t. But we can say, okay, we know that the sine function at any angle theta is 1/2 when theta is equal to pi over 6 or 5 pi over 6, right? And remember, we just did that here in this first example. So we know pi over 6 and 5 pi over 6 will satisfy sine being equal to 1/2. So now, how do we work with when you have pi over 12 times t for that theta here? So let's take a look at this explanation here. So we are saying, okay, so while we know that we have these specific angles pi over 6 and 5 pi over 6 that have a sine value of 1/2, because of the horizontal stretch or compressions, it is less clear how to proceed. So we know because of this pi over 12, we are looking at it should be a compression. Yes, I believe it will be a compression. So how do we deal with that. So that's the next part here. So let's take a look at it. So we're saying to deal with this, we need to make a substitution. And in official terminology, guys, we would call this as U substitution because you're using the variable U to temporarily replace pi over 12 times t. So you will have sine of U equals 1/2. So you're basically just taking this and replacing it with U. So sine of U is equal to 1/2. And then we know that U can be pi over 6 with the coterminal values added to it. So, right, so it could be pi over 6 plus 2 pi k, or it could also be 5 pi over 6 with 2 pi k. So now let's simplify that. So you will actually have and you can see, of course, k is an integer. So now we will say, okay, we know U stands for pi over 12 times t. Now we want to actually figure out what t is going to be. So in both of these equations here, guys, we now replace the U with pi over 12t, replace this guy with pi over 12t, and then basically we want to try and get the t by itself. So it looks like they kind of just skipped over. It's not hard to actually get that math, but I just want to show you how to get there. So remember, our goal is to get t by itself. You can do this in one step or two steps. It's up to you. But basically, to get t by itself, we want to get rid of that fraction, which means we can multiply both sides of our equation by inverting pi over 12 so that pi and pi can cancel out. 12 and 12 can cancel out, giving you t on one side. And then, of course, we will distribute this fraction inside of the right-hand side expression. So as you can imagine, when we multiply pi over 6 with 12 over pi, some of those will cancel out and simplify. And then, of course, with the 2 pi over k, we'll do the same thing. So pi and pi, as you can see, will cancel out. 6 goes into itself once, goes into 12 twice. So you can see that first term just ends up becoming 2. And then on the second expression, the pi will cancel out. You're left with 2 times 12, which will become 24. And then, of course, we have the k. So you can see that's where t equal to 2 plus 24k is coming from. Again, k is an integer. Now, if we had to do this with the 5 pi over 6, we can actually just kind of modify this guy. Okay, so trying to use a different color so I can show you just a quick difference between the calculations here. So the only thing that will change is instead of pi over 6, we had 5 pi over 6. So you will, of course, then end up multiplying 5 times 2, which will replace this guy with 10, but you will still have 24k for the other half. So you can see that just ends up becoming t equals 10 plus 24k, where again, k will be your integer. So you can see T, remember, told us that it was the time in hours after midnight. So if you just look at the very first line of the problem, it tells us T is measured in hours after midnight. So we have two different values for T once we simplified this. So we are saying, okay, the depth will be 9 feet and the boat will be able to approach the dock between 2 a.m. and 10 a.m. because remember the 2 represents how many hours after midnight. So if midnight is your starting point, that's your 0 hour, right? So midnight becomes 0. So the 2 tells us it's going to be 2 a.m., 2 hours after midnight. And the 10 in the other time tells us it's 10 hours after midnight. So that's going to be 10 a.m. And as you can imagine, the 24 represents a 24-hour cycle, right? So give or take a day. But basically, we're saying anytime between 2 and 10 a.m. on any given day, the depth at the dock will be 9 feet, which means it's safe for the boats to dock at the at those hours, right? So the only thing that happens here, guys, is because this was not a generic scenario, we did have to figure out what the specific value would be. So you can see we started out with, okay, let's get sine by itself, which we did, which led us to this equation. Now we know for angles pi over 6 and 5 pi over 6, our sine value would be 1/2. But that's not enough to just solve for the time, right? Because remember, right now we just have the angle for the sine function, but we need to solve this in terms of time. So this is where that idea of u substitution came in place. Now, if you wanted to skip the u substitution part, you could. I just find that it makes it easier because then we're not looking at, too many of these fractions and pi's and values of that sort. So we know it's going to be pi over 6 plus the 2 pi k, and 5 pi over 6 for the 2 pi k, where our sine function is going to be equal to 1/2. So instead of the u substitution, now we go back to the original angle, which was the pi over 12t. So we go ahead and now replace that in our equation here, solve each one of these for t like I showed you. And then once you have your t simplified, remember t is now the time that we were looking for. And then based on the example, we are able to come up with our answer. And I love that they included the graph over here because you can see the horizontal axis is giving us the time, and you will see this does start at midnight. So this here actually is 0 hours, which would be midnight. And then you can see, of course, we're going on a 24-hour cycle here. The vertical axis is giving you the depth at the dock. So if you look at this guy here, you will see right at 2 a.m. is where our graph is curving upwards, right? And it goes on till 10 a.m. So you can see between 10 and 2 a.m., this is your 9 feet line. That dotted line represents the 9 feet. So you can see before 2 a.m., the water is too low, so you will not be able to dock the boat. And after 10 a.m., of course, again, the tide changes, right? So you can see we're not going to be able to dock. So yeah, exactly between 2 a.m. and 10 a.m., it's safe for the boat to dock. So visually also, we can verify that information. All right, guys, did anybody have any questions on this? Okay, and we'll definitely take a look at an example for us to solve to make sure that, we can get some practice in ourselves. Now here they're saying, looking at the previous example, at the original simplified equation where we had sine of pi over 12 times t equals 1/2, we used the ratio of the normal period to the stretch factor of the to find basically the new period for the function, right? So remember when we first talked about the b value calculation, that's kind of what they're going back to here, where we had the period equals, what was it, 2 pi over p. That's what you're exactly doing here. So you've got 2 pi over this b value of, oops, what's going on? There we go. Pi over 12. So again, you are changing that from division to multiplication. So if you have 2 pi divided by pi over 12, change that to multiplication, flip your fraction, and you get 12 over pi into multiplication. So that's where this guy is coming from. Of course, your pi and pi will cancel out, and 2 times 12 is giving you 24. So basically, they are saying in that previous example, you went from an original sine function having a period of 2 pi to this specific dock and boat example having a period of 24, which is also why you will notice why we were adding 24K with both of these timestamps over here, because that period changed from 2 pi to a 24. So they are saying you have two unique solutions on one full cycle of the sine function and additional solutions based on, when you do the multiples of the 24K to get, the different days, different values for t, but it would just be based on whatever that k value is going to be. So yeah, you basically did the uh, b equals 2 pi over p or p equals 2 pi over b calculation here to figure out what the new period for that function was going to be. So kind of tying back to, everything we saw at the beginning of this chapter. Another example over here, guys, but we're keeping it generic now because they are asking us for all possible values of t. So we're not doing for a specific time frame. You are given 4 sine of 5t minus 1 equals 1. So again, you will see you need to isolate that sine function. So you can start by adding that 1. So 1 plus 1 will give us 2 on the right-hand side. And then to get sine by itself, we will divide both sides by 4. So you can see 4 and 4 will cancel out. And that's where you got sine of 5t. 2 divided by 4, of course, reduces down to 1/2. So that's how they came up with that equation. So move the 1 to the other side, divide by 4, and you have your simplified function. So we'll notice again that we went back to sine of 5t being equal to 1/2. So we know the sine function is 1/2 at these two angles, pi over 6 and 5 pi over 6. We know the original sine function has a period of 2 pi. So you can see we add 2 pi k to both of these angles. Now we are going back to using the u substitution. So you can see we are saying let u equals 5t. And then once you have these equations over here where you have u equals pi over 6 equals, sorry, not equals, but plus 2 pi over k. And then the other one, of course, will be u equals 5 pi over 6 plus 2 pi over k. Once you get to this stage, then we can go back and undo the substitution in a way. And instead of u, you can now replace it with the original value, which was 5t. And then basically get t by itself. So since you are multiplying t with 5, that of course tells us we need to divide everything by 5. So however you want to do it, that seems convenient. You can divide by 5, or in my case, I would probably multiply it by 1/5 because it'll be easy to work with that first fraction. So same thing here, multiply both sides by 1/5. Of course, these guys will cancel out on the left, leaving you with just t. And then as you can see, when you distribute this in the expression on the right, you will get pi times 1, which is pi. On the denominator, you are doing 6 times 5, which will give you 30. So you can see that's where this expression is coming from. And then, of course, the 2 pi k multiplied with 1/5 will, of course, just give you 2 pi over k divided by 5. So that's where this first term is coming from. When you distribute this 1/5 in the second equation, since you had a 5 on the top, it will cancel out. So that's why you are only left with pi over 6 here. And then same thing, 2 pi over k multiplied with 1/5 will, of course, give you 2 pi over k, 2 pi k over 5. So same exact process. The only difference is, you were not doing it for a specific time of the night, but process honestly is exactly the same if you were doing the doc example or you're doing this generic example. So you can see how that u substitution is working out in both instances. Questions on this one here, guys? Okay, let me see if we can find a similar example from our exercise. This is for a specific interval. Let's do number 9 from our exercise section. All right, so you are given 2 times cosine of theta is equal to square root of 2. And remember, this is saying all solutions, which means we will need to consider the period for the cosine function. So just like we did with the previous examples, you want to get your cosine function by itself, right? So since you have 2 times cosine of theta, you will need to divide both sides by 2. So you can get cosine by itself. So that's the easy part. Now, take a minute, look through. I believe you should be able to find the answer on the unit circle. Look through and tell me what the value of theta should be, where the cosine has square root of 2 and 2 as its value. And again, guys, when you share your answer with me, just make sure you're not sending it to everyone, but directly to me, because I want to give everybody a chance to look through that. So for what angle theta is your cosine value square root of 2 over 2? Okay, I'm seeing something come through here. Okay, Zadok, is there only one angle for the entire unit circle? Because remember, they're telling us all solutions, right? Which means we've got to find all the possible answers. And if you guys want, I can actually share the unit circle here with you, but I don't know how well you will be able to see with the writing on there. All right, Zadok, I see your other answer. Very nice, very good. Anybody else? Logan, I see yours. Okay, so Logan, I'll tell you one of them is correct, one of them is not. So think about it. Your cosine, and I know it's hard to see, but the cosine value should be positive square root of 2 over 2. All right, there you go. You figured it out. And Bailey, yes, very good. Very nice. Anybody else want to try giving me an answer? Okay, sorry, I will go back. Um, so Zadex, since they are asking specifically for all solutions, you are looking at all quadrants. Yeah. So you want to go to all 4 quadrants and see where you might find an angle that would satisfy our function. So yeah, very nice, guys. All right, perfect. So where is our cosine function with a value of square root of 2 over 2? And that's positive, right? So you can see here, our cosine value is positive square root of 2 over 2. So that's the angle pi over 4. And then the one other answer is in quadrant 4. So you can see again, our cosine was a positive square root of 2 over 2 at 7 pi over 4. Now, if you look at, and I'm just going to delete this for a second so I can show you. If you look at quadrants 2 and 3, you can see the cosine value is actually negative, right? It's negative square root of 2 over 2, negative square root of 2 over 2. So that's why angles 3 pi over 4 and 5 pi over 4 will not work for this specific example. So yeah, it's quadrants 1 and 4. And let's bring back our problem here. So very nice. The first one was pi over 4 and the other angle was 7 pi over 4. But again, since they are saying all solutions, that means you are going to be adding coterminal angles, right? And remember, the period of a cosine function is 2 pi. So you will be doing 2 pi k to get, as you go, uh, well, rotating, moving around the circle, however you want to say it, either in positive or negative direction, will get all the coterminal angles. Does that make sense? Yeah? Okay. And you can see there are a bunch of different examples over here that if you wanted to practice, that you can. So, some of these here are keeping it within a specific interval. So let's say if we did something like, well, you know what? Let's do number 5 very quickly. So you can see for number 5, they have sine of theta is equal to 1, but you will see they are saying all solutions, but within the specific interval, right? Which means you're only keeping one rotation of the circle. So where is sine of theta equal to 1 at? And if you come and look at the unit circle, you will see sine of theta sine value is equal to 1 right here when you are at pi halves, right? This is sine of 1. And that's it, right? None of the other values for the sine function are going to be positive 1. So for this one, since they're specifically asking us to stay within that first interval, you will do pi halves, but you will not be doing any 2 pi k here because you only want to stay just one rotation. And once you come back from 0 to 2 pi, you stop. Am I making clear the distinction between what they wanted here and there? Why we're not doing 2 pi k in this number 5 example? Because when they restrict your interval, you will not be using 2 pi k. Okay, when they just leave it open, like find all solutions and no restriction on the interval, that's why we did the plus 2 pi k here, but you don't do that up here. Okay, all right, guys, stay back if you have any questions, but we'll pick up from the remaining half of this section on next class. Remember, you guys are wrapping up section 2.3 this week. And again, do not hesitate if you have any questions, okay? Enjoy your evening, everyone. Take care. Bye-bye.